right, wonderful. We have Neel joined now. That's perfect. We're just waiting for him shortly. Let me see here. Perfect. Greetings, Neel. Glad to see you. All right. So, I'll just focus on myself, shall we? Welcome to this month's Alignment Jam, and what a great turnout in general internationally, and a few here, which is wonderful. I'll just shortly introduce Neel Nanda and get him inspiring us, and then afterwards I'll introduce a lot of the logistics about the hackathon and about the Alignment Jam in general. But first, let me just introduce our keynote speaker. So, Neel Nanda he has worked with Anthropic and Chris Olah on making transformers interpretable in their interpretability team. He has released the Transformer Lens library, or the Easy Transformer library earlier, which is a wonderful open source tool for mechanistic interpretability and some of the state-of-the-art work in there. He has done a bunch of amazing work and shared and released a lot of his work publicly for everyone to enjoy and to use, along with a lot of YouTube videos, which are amazing. And then he's, of course, always wonderfully kind and amazingly helpful to join us here and share all his great knowledge with all of us. So thank you, everyone, for joining. And thank you, Neel, for giving the keynote speak. And I'll pass it over to you.
Hey. Thank you for the extremely kind introduction. So this is going to be a whirlwind tour of a sequence I wrote called Concrete Open Problems in Mechanistic Interpretability. A bunch of links, so if you want to follow along at home, you can see the slides here. And you should mostly ignore the rest of these links and check out the quick start guide that I wrote that Esben kindly shared on the announcements channel. Yeah, so in brief, what is mechanistic interpretability? So the core goal of mechanistic interpretability is to take a neural network and try to reverse engineer what it's doing. In particular, we take a network when we know that it performs well on a task, but not how it performs well on the task, and then we try to understand what the underlying cognition is. What are the algorithms the model has learned? And one core reason I think this is super important is that this should allow you to distinguish between multiple possible solutions the model has learned. And when we're trying to think through how to align models that are human level or above, this is particularly concerning because you gradually converge on the world being such that there are two equally valid solutions. Be extremely competent at being deceptive and actually be aligned and helpful and try to do what your users want. And yeah, the focus of this is not going to be on questions around alignment relevance, but that is my very brief take for why you might care about this. And you should check out this post from Chris Olah for my current favorite deeper take. And here's a cute example of what this kind of thing can look like. This is a small circuit that is a subpart of the network implementing some specific part of an algorithm in an image model that is being used to... so this is an image classification model. These represent 3 neurons, which seem to be detecting car windows, car bodies, and car wheels. There's a later neuron that detects cars, and these are the weights. That's how the car detector is built from these simpler neurons. And I'm going to be referring to circuits a bunch in the rest of this presentation, but the general vibe is sub-bits of a model that fit together to perform some part of an algorithm. And yeah, a bit on why I think you might be interested in mechanistic interpretability, or at least why I'm excited about it. So the first is I think it's unusually easy to get started in compared to other areas of alignment. It has pretty great feedback loops because you're not thinking through high-level, thorny philosophical questions. You're playing with a real system, and you're trying to form true beliefs about that system. And this means you can run experiments and get feedback from reality. And I just find this incredibly fun. I'm a pure mathematician by background, and to me the vibe of doing mechanistic interpretability is some combination of maths, because fundamentally a network is a mathematical object doing a bunch of linear algebra, computer science, because reasoning through algorithms, how the model might implement these things, and just conceptually what should I expect to happen, natural science, because in some sense, a network is a weird, confusing alien organism that I am trying to investigate and understand. And finally, truth-seeking, because the fundamental goal is forming true beliefs about this network. And there is a ground truth to be understood, if I can find it. And yeah, one central bit of advice I want to give is to code early and code a lot. This is a hackathon, so you should basically aim to spend most of your time coding and some of your time learning. A very common mistake I see in people trying to get into the field is thinking they need to read the entire literature and they need to understand every last detail and explore all of the papers, etc., etc. And I mostly think this is a mistake. I think that one of the best ways to learn is to just jump in and write a bunch of code and see what breaks and iterate. And finally, I don't want to kind of over-egg the it's easy to do this research and it's easy to get feedback loops. One of the core challenges, and in my sense one of the most fun yet frustrating parts of working in MechInterp, is that it's easy to have false beliefs about the network. It's easy to think there's something really complicated going on and miss a simple, trivial explanation. And part of the joy is being a scientist, trying to break your beliefs, trying to falsify things, and trying to understand what you've gotten wrong. And yeah, so a brief whirlwind tour of what a transformer is. Transformer being the neural network architecture that underlies language models. And most of the areas I talk about in this presentation are going to be language model focused, because that's the area I work in and what I think is most relevant to alignment. You should check out my What is a Transformer tutorial that's linked in the Quick Start Guide for a deeper dive, but I'm just trying to convey the basics. Fundamentally, the input to a transformer is a sequence of words, and the output is a probability distribution over the next word. These models are trained by just giving them a massive corpus of text, like the entire internet, and training them to predict the next word. Notably, for every word in the sequence, the model is trying to predict the next word. And it's set up internally so information can only move forward in the sequence, so this is not cheating. But this means that if you give it 1,000 words, it's getting 1,000 bits of feedback, because it's predicting 1,000 next words. Technically, it's predicting tokens, not words, which are kind of subwords and are a massive pain, but thinking of them as words is a good enough high-level intuition, though you're really going to want to understand tokenizers, depending on exactly what projects you choose. The central bit of the model is the residual stream, represented by this line. For every word in the sequence, after every layer, there is a representation of that word. And intuitively, the stream represents the word plus surrounding context. And after every layer, the residual stream gets incrementally updated. So it's the sum of all previous layer outputs. And you can kind of think of each layer as incrementally building a deeper understanding of what the relevant word is, integrating more and more context, until at the end, it can be converted into a prediction of what comes next. There are two types of layers that update the residual stream. The first are these attention layers, which move information between words, but mostly focus on copying the information and on figuring out which words are most relevant to the current word and what information to move. It's made up of several heads, represented by these blocks, that each act independently and in parallel. Independently, meaning each head can be thought of on its own, and in parallel, meaning each head is independently choosing what information to move and where from, and the output of the layer is just the sum of each head. Generally, a lot of the work in the field has been focused on interpreting specific heads and the circuits by which they fit together. And the second type of layer are these MLP layers, which stands for multi-layer perceptron, which is jargon for the kind of simple neural network that you might have learned about before. And MLPs process information once the attention layers have moved it to a specific word. Check out these walkthroughs below if you're interested in getting a deeper understanding. This is a kind of 1 hour, more in-depth tour of what I just did here. This is a 1 hour tutorial of how you can actually implement GPT-2 for yourself from scratch, complete with a notebook that comes with tests. So this is hopefully a lot easier than doing it yourself, than doing it completely with no guide. Okay, so now I'm going to pivot to a whirlwind tour of areas of open problems. The thing I want you to take away from all this is not an in-depth understanding, because each of these categories will correspond to a post in the sequence you should go read for actual context. I want to convey the vibe of what the area is about and why you might be excited about it. This also means that if you zone out or get confused in a particular area, you can just zone back in at the next one. Alright, first area, analyzing toy language models. So a toy language model is a language model that's exactly the same as an enormous one like GPT-3, but rather than having 96 layers, it has 1 layer, or somewhere between 1 and 4 layers, and sometimes it will only have attention layers rather than attention MLPs. It is otherwise trained in exactly the same way. And you can kind of think of these as a simplified microcosm of a full real language model. That's as close as we can get it, but small enough that we can get a lot more traction on understanding them, and which, in practice, seem to actually model some deeply true things about real networks. One of the most striking examples of this are induction heads. Induction heads are a small 2-head circuit we found in 2-layer attention models. Again, by circuit, what I mean is 2 heads working together to complete some overall algorithm. And what induction heads do is they use knowledge in the past to predict what's going to come next in the sentence by observing that text often contains repeated strings. Like, you've got a forum thread where someone's quoting a comment above, and the induction head checks, has the token I'm currently on come up in the past? If so, what came next? Let's predict that comes next. And on first glance, this doesn't sound incredibly important, but induction heads turn out to be a really big deal, to the point that we wrote a whole other paper on them. And one of the most striking things is that induction heads are A, universal, meaning they occur in every model we've checked up to 13 billion parameters. 2, induction heads are crucial to this weird behavior of transformers called in-context learning. The idea of in-context learning is that models can use words that are far back in the context to predict what comes next. This is a kind of weird and surprising thing models can do. It's analogous to taking something that's 4 pages back in text in order to predict what comes next, yet models can do it. And the third wild thing about induction heads is they all occur in the model in this narrow band of training we call a phase change. And here we've got 1-layer, 2-layer, and 3-layer toy language models. And we see that the 2 and 3-layer ones have this narrow band of training. They suddenly get good at in-context learning, and also suddenly develop induction heads, and the 1-layer one just doesn't. And you can also understand induction heads in a bunch of detail, at least for this specific behavior of strict induction, of check where the current token appeared in the past and look at what comes next. I'm not going to go through this, but you can check out this blog post for more details and digging more into this great diagram. Alright, pivot area. A specific example of a problem that I would love to see someone try to get traction on is to try to reverse engineer a specific neuron in a 1-layer language model, which which includes the MLP layers. No one has done this. I don't expect this to be that hard. I'm reasonably confident there'll be neurons corresponding to things like trigrams, like the word ice followed by the word cream triggers a neuron which predicts that Sunday or parlor will come next. And I just think this is probably doable, but no one's tried that hard. And in the quick start guide and the accompanying post, I link to some resources with my Transformer Lens library where you can actually load these models and play around with them, and where I demonstrate some basic techniques. I believe that Stefan Heimersheim, one of my mentees, has also linked to a blog post he's writing in one of the channels on here, where giving some further resources for doing this kind of project. Alright, pivot to Area of Concrete Open Problems 2. Looking for circuits in the wild. The goal of this one is to take the same kind of mindset we were applying to toy language models and try to apply this to real language models, where they're not kind of super tiny models trained specifically for interpretability. They're kind of larger and messier, not necessarily kind of up to the size of GPT-3, because that's just a massive, massive pain to do, but I think that just trying to make some real progress on interpreting something like GPT-2 small is likely to teach us cool and real things. And the work that most inspired this section is this great paper called Interpretability in the Wild from Kevin Wang and all at Redwood Research. They interpreted how GPT-2 small could solve the grammatical task of indirect object identification. This is when you have sentences like the above, where you've got two names, and the next sentence, name 1, blah blah blah, and it needs to be followed by name 2. It needs to be followed by Mary, not John. And they did a heroic amount of reverse engineering, and found this complex and sophisticated setup where there's this 25-head circuit that breaks down into discrete parts. This cluster of heads detects that the John is the duplicated token. These S inhibition heads move that to the position at the end. Remember that the model has a separate residual stream representation at each position, so moving things around is important. And then these heads attend to every name that is not repeated, and thus look at Mary. And this is just a complicated but legible and reverse engineerable circuit that they found in GPT-2 small. And I made a demo that I call Exploratory Analysis Demo, where I try to speedrun discovering this circuit, starting with just the knowledge that the model can do this indirect object identification task. And one great thing about trying to build on prior work is there's often demonstrations and code that you can just copy, and existing techniques you can just try to use. And a concrete problem that I think might not be that hard to do here is to try to check how universal the IOI circuit is. If you look in, say, the smallest version of OPT, or in one of the Mistral models included in Transformer Lens, does the circuit look the same? And as a brief overview of the kind of techniques you can use to really get traction on these kinds of questions, there's this technique I love called activation patching. The idea of activation patching is that you've got two inputs where the model does two different things. Say, the Big Bang Theory premieres on CBS is something the model knows, but if you do a bunch of stuff to corrupt the Big Bang Theory tokens, then the model no longer knows it's CBS because it can't figure out what this noun is. The idea of activation patching is you pick a single bit chunk of the model, and then you copy that chunk from the clean input, where it gives the correct output, to the corrupted input, and you intervene on the corrupted run where you just replace that input. And then you check, is this enough to flip it to the correct output? And it turns out in practice that this just often is. Here's a heat map of every head in GPT-2 Small, where I tried doing this, giving it an input where it gave the correct answer on the indirect object identification task, and an input where it gave the incorrect answer. And this shows that each of these heads is kind of sufficient on its own to get some meaningful traction, to like meaningfully flip the model's output from incorrect to correct. And A, it's just kind of wild that individual heads are sufficient on their own to contain this information. And also B, this is just like a pretty simple technique that there is code that just implements it in this demo. And you can just apply it on the IOI task or any other task you care about and get traction on figuring out what the model is doing. It's great. Alright, pivot to next area, training dynamics. So it is just a weird fact about the world that neural networks are capable of generalizing. You just keep making tiny incremental updates to their parameters so they perform a little bit better on each training example. And each of these is just a tiny incremental change that makes the model slightly better. But at the end of training, it's capable of doing often really weird and complex tasks, like explaining jokes. That does not seem like a thing that you should be able to get with small incremental updates. And I think that trying to reverse engineer a network and trying to study what happens during training could significantly demystify things. A concrete example of some work I was involved in here is, so there's this phenomena called grokking, discovered in this OpenAI paper. They train a small model on an algorithmic task, here modular division, and they let the model look at half the data. They find that initially the model just perfectly memorizes the data it sees, and does terribly with the data it hasn't seen. But if you keep training it for a really long time, 100 times as long, it eventually suddenly generalizes. And to note, it never sees any of the data it suddenly generalizes on. It just looks at the same data again and again. This is really... And some work I was involved in, we trained a model to grok modular addition, and then we fully reverse engineered the underlying algorithm the model had learned, where it learns this extremely legible and interpretable, yet also wild, geometric algorithm based on Fourier transforms and triggered entities, where it realizes the modular addition can be thought of as rotation around a circle. It converts the two inputs to rotations by angles A and angles B. It composes the rotation to get the rotation A plus B, and then it reverses this by each possible output angle C, and looks at what that does to the x-axis. And the x-axis is biggest for the rotation that is do nothing, i.e. C equals A plus B, and you get the modular part because circles wrap around. And hey, it is just wild that models do this. What the fuck? But also, using this understanding, we can just look inside the model during training. The graph on the right is the loss curve. The graph on the left is how much the model has learned the different frequencies that it might rotate by. And we can see, well before the point where it actually generalizes, it's significantly learned the correct angles. There's also some really weird stuff. Like it, despite having already generalized, it unlearns some angles, and it learns some more angles. The fuck? A concrete problem here that I think someone could tractably work on is, I showed that grokking can happen in a toy model that I trained to have induction heads, and managed to get it to grok. Can you properly reverse engineer what the model has learned? And can you use this to look at how it develops during training and design some analogous graph to this? I also trained a model to grok 5-digit addition, and found that it had a separate phase transition where it learned to generalize each of the 6 output digits, and that it had also seemed to learn some variant of this modular addition algorithm. And I'd also love to see someone reverse engineer that. Alright. Concrete open problem area 4. Studying neurons. Or, more specifically, studying what kind of features have been learned and reverse engineered in language models. What kind of features the model has learned, such that we might be able to reverse engineer it. There was this really great paper called Multimodal Neurons, which studied this model called CLIP, which learned to caption images. And they found that because it had this image input and this text input, it had learned a bunch of neurons that seemed to be putting things into this very abstract conceptual space. By looking at these neurons, they found some wild neurons, like a Donald Trump neuron, or an anime neuron, or a teenage neuron, or a crying neuron, or a West African neuron. And I'm really excited to see just even like fairly qualitative work like this, just cataloging what kind of features arise in language models. And there was this paper I was involved in called softmax linear units, where we found a variant on a transformer that seemed to make the neurons a bit more interpretable, and went and looked for a bunch of neurons that seemed to have some meaning. And we found things like this A64 neuron in a one-layer model, which noticed that, there's often, I don't know, compressed links with base64 text after them. What's up with that? And that this neuron boosts things that are rare tokens that appear a lot in base64. Or disambiguation neurons. The input to the model is just kind of each word or each token. But the token D means very different things in different languages, like Dutch, German, Afrikaans. It also means very different things in English, whether it's death or dice. And the model learned separate neurons to disambiguate this, because it wants to treat the token completely differently. And then, if you look at middle layers, there's some wild conceptual neurons. This one describes numbers that implicitly refer to groups of people, and not to other kinds of numbers. And I made this tool called Neuroscope, where I created things like this, which show the text that most activates every neuron in a bunch of language models. The website is currently slightly janky, and also I ran out of storage this morning, because apparently my website only gives me 120 gigabytes of storage, which is extremely stingy. But it is usable, and you can go through a bunch of models and look at the neurons. And I would love to just see people, A, catalog what kind of wild things you can find. In particular, looking at the middle layers of the larger models, like GPT-2 XL, or a GPT-2 Large, or a GPT-2 medium-sized Soli model that I trained, and trying to just catalog what kind of weird features arise. And in the relevant post, I also link to an interactive Neuroscope that I made, where you can just type in text and live see how much the neuron activates. And I would love for someone, I think a great project would be to find some wild neuron, like this, and then just type in a bunch of text, and see how much you can refine your hypothesis of what it actually does. This basically requires writing no code, but I think can be a great way to build the kind of empirical mindset and skill set. Next area of concrete open problems. Again, if you've zoned out, you can rezone back in. Polysemanticity and superposition. So, a problem with the area I just outlined, of looking at neurons in order to find features, is that sometimes models do this really annoying thing called polysemanticity, where one neuron represents multiple features. This is an example from the Multimodal Neurons paper, where they found something which represents both poetry and games, like cards, the word game, poker. And this is really annoying. What's up with this? Can we better understand what's going on? And one hypothesis is that models do superposition. The idea of superposition is that models sometimes want to simulate a larger model with more parameters, because more parameters means you can do better at a task, and more neurons means you can have more features. And they learn to use superposition, which is when they compress this large number of features into a lower dimensional space. And this is just kind of wild. And this great paper, Toy Models of Superposition, just built a really simple model of this phenomena and found that you could get models to compress things in certain situations. This is a pentagon compression, where the model just fits 5 features into 2-dimensional space. And it turns out these geometric configurations are everywhere. If you train a model to compress 100 features into 20-dimensional space, and you vary how prevalent the features are, it turns out the features spontaneously self-organize into different subspaces, where you have, say, triangles with 3 features in 2 dimensions, and then some other things that sort into antipodal pairs with 2 features in 1 dimension, or pentagons with 5 features in 2 dimensions, or tetrahedra. It's wild. And I think there's some great work to be done, both digging further into their toy models. I'm particularly excited to see more work on neuron superposition, which is where you have the equivalent of an MLP layer, where the model is trying to compress more features than it has neurons, and also to see empirical work trying to test the predictions of this paper in real models. In particular, it predicts that important features should have dedicated dimensions that are monosemantic, because the really important features, you don't want to have the weird interference you get with compression. Positional information gets dedicated dimensions in the residual stream for most models. Is it the case that these are monosemantic directions? Or is there a lot of interference? Just doing something like a singular value decomposition on the positional information, looking at the dimensions which are most important for that, and then checking whether other things write to that area of the residual stream, I think could be a really cool project that might be doable in a weekend. Pivot. Next area of conquer different problems. Techniques and automation. So, fundamentally, the goal of mechanistic interpretability is to form true beliefs about networks. And to do this, you need many things. But in particular, you need a good toolkit for what kinds of things you should do when you see an unfamiliar network, and what kinds of things and what techniques you should use, what those techniques tell you, and even more importantly, where those techniques can break. And in the Interpretability in the Wild paper, they found this fascinating phenomena of backup heads. So, a classic technique in interpreting networks is this idea of ablation. Ablation is when you pick one bit of the model, in this case, attention head, and you set it to 0. And you expect that unimportant things, setting it to 0 doesn't matter, important things, setting it to 0 matters a lot, and will totally break things. But they found that taking heads they knew to be important and setting them to 0 didn't really change things. And when you dig into it, it turns out there is this redundant backup behavior. This graph shows the direct effect of each head on the final output, before and after deleting an important head. The important head's up here, it goes down to 0. But these 2 heads move significantly off the diagonal, showing that they deliberately change what they're doing to compensate. And I would love to... Yeah, my demo involves replicating this result, which is where I took that graph from. I would love to see if there are other backup heads, like backup previous token heads or backup induction heads. Another area is that of automation. A lot of mech-interp is pretty labor-intensive. I personally think this is a lot more fine than most people do, because I think we're a lot more bottlenecked by true beliefs about networks than by really scalable ways to extend our true beliefs about networks. But I still think that having automatic tools we can apply to a new network to better understand it would be awesome. And here's this thing I made that I call an induction mosaic, where I just ran every head in 41 open source language models on sequences of repeated random tokens. Induction heads work on repeated random tokens And you can use this to automatically identify the induction heads by checking for whether they attend to the token after the first copy of the current token. And this means you can give each head a score for how induction it is. And I made this mosaic, which is just a heat map of every head, y-axis is head, x-axis is layer, in the 41 models in my Transformer Lens library. The same code ran on all of the models because of how I wrote the library, and we can see that induction heads are everywhere. And we can also notice some weird things, like GPT-J has induction heads early on. Every other model doesn't. I think a great project would be making a kind of wiki for heads, where you do the same mosaic for some of the other heads we understand, like previous token, duplicate token, heads in the IOI circuit, and just make a bunch of mosaics like this, or make a massive pandas data frame which just has all of these scores for heads. Pivots. Next area of concrete open problems. Interpreting algorithmic models. So, kind of the even more toy version of the looking at toy language models trained on real language data, but much smaller than the real models we care about, is training a model on an algorithmic task and trying to reverse engineer it there. I think this is, in some ways, just less exciting than interpreting real language models, since the results are more distant. But I also think there's pretty cool things about it, and that it's really accessible if you're just kind of getting started and want to work on something clean with a ground truth. And I also think it can be pretty great, because it serves as a test bed for interpretability tools. We can just check if our techniques are good, they should work for these toy models. It can build toy models of things we want to understand better. For example, GPT-3 can do addition. If we build a algorithmic model that does addition and try to reverse engineer it, hopefully my modular addition algorithm comes up. This could better instruct us on how to find it in GPT-3. Or the toy models of superposition work that I mentioned before. And yeah, particularly easy to get started. And for this, I made a different demo, which was an experiment in recording myself doing real-time research, where you can watch the video here and see an accompanying notebook. The goal of this experiment was we explicitly give language models positional information, telling them which position they're at. But in some sense, this shouldn't be necessary, because the fact that models can only look backwards means it can tell the difference between different positions, because the kth position can see k previous positions, even if we don't explicitly tell it where it is. And so I just trained a model, stopped it from getting any positional information, and trained it to predict the previous token. And this is the attention pattern of the second layer head it learned, and you can pretty clearly see it's learned to attend to both the token and the previous token. And I got part of the way through re-deriving what was going on there. I think a cool project would be finishing that off. And there's just like a bunch of other ideas. Here's a bunch of resources to learn more. The quick start guide that's linked in announcements that Esmond can hopefully repost tries to give a bunch of more concrete advice and details for how to get started, how I think you should adapt to the advice in my sequence, which is more about longer-term projects for a weekend hackathon. But yeah, more generally, I have this post called Getting Started in Mechanistic Interpretability, where I try to lay out how to build the key prerequisite skills and the best resources. I have a glossary and explainer where you can look up any confusing terms that I've mentioned or that you see in the reading or in various papers you check out, and with long digressions to build intuition and flesh out what earth's actually going on, and this Transformer Lens library that I made that I expect is going to be the most useful tool for basically all of the projects I've outlined, that lets you load in most open source GPT-style models, run them, cache what's inside of them, edit the activations, and has a bunch of other quality of life improvements an accompanying tutorial and code to crib from, and generally tries to make it so that the things you want to do are easy, and you can spend more time actually doing research and thinking, rather than several weeks setting up infrastructure, as I had to do when I started doing independent research. And yeah, just closing with some thoughts on how I recommend orienting to a hackathon. So, as I've tried to emphasize, I think that the bar for entry for mechanistic interpretability is significantly lower than most people think it is. I also think that it's kind of higher than you can reasonably cross on a weekend. So the thing I recommend orienting to this weekend as is get your hands dirty, jump into a real problem, try to learn as you go, and try to get some momentum and get some traction, and just like get excited about something and see how far you can get. But where if at the end of the weekend you've had a lot of fun, got stuck a bunch, been very confused, had occasional moments of insight, and learned a lot, that's a pretty great victory. And I think you should be pretty happy with that. And yeah, I think if you're doing a longer-term project, you should go check out my Getting Started guide. But this is a hackathon, you want hackathon energy, pick something you're excited about, don't overthink getting the perfect problem, just jump in, and dip into the resources I catalog in the Quick Start guide for just advice and deconfusing yourself as you go. Yeah. Thanks very much to Esmond for inviting me for this keynote, and good luck. I'm really excited to see what people come up with this weekend.
Wonderful.
And please do raise GitHub issues or DM me complaints for the no doubt many bugs you will find in my resources.
Thank you so much.
Feedback is extremely welcome.
Yeah. Perfect. Let's give him a hand. Thank you so much, Neel. And if anyone has any questions, they can post them in the chat, and Sabrina will look out for them and possibly turn on her microphone and say them aloud. Otherwise, I can start out with a couple different ones. So
sure.
I
should also say I love people having videos on, so I feel less like I'm talking to a blank screen.
Yes, that's perfect. One video on.
Take it.
Wonderful.
Yes.
Yeah, I guess the first question I'm curious about, now we've talked a lot about language models and transformers and so on. Mm-hmm. Do you think some of the other fields, like what are your views on some of the other related fields where you might apply some approaches of mechanistic interpretability to understand different algorithms in, for example, vision models? Like, how are you looking at that from both an alignment, but also just a mechanistic interpretability interest perspective?
Sure. So I do have posts in the sequence on interpreting image models and on interpreting reinforcement learning. I think that both of these are cool areas that are not the areas I work in, so I'm less confident talking about them, and I have many fewer resources for people to get started with. So that's the main reason to focus on them. In general, please take all of my resources and pointers and my list of open problems as starting points. But like, prioritize, do things you're excited about, be ambitious, see how much progress you can make. Yeah, more generally, my guess is the most likely way for us to get AGI, at least if it happens kind of within the current paradigm of deep learning, is via something that looks something like large language models. So no doubt with like a bunch of weirdnesses and changes. And this means that I'm most excited about interpreting language models. Also just because they are the most powerful models we have today, and I think that one of the best ways to alignment work, especially if you want real feedback loops and empiricism, is to practice as hard as you can on the best systems we have today. I'm also particularly excited about work interpreting reinforcement learning, the study of how to train models to optimize some reward or some utility function you give them, which can involve things like multi-step planning, having goals, reasoning about the environment and forming internal models of it. I expect interpreting RL to be harder, and harder to get traction on in a hackathon, I think there's some really cool ideas in there. And there's some things that you might actually be able to get traction on. Generally, anything which involves training a smaller model, plausibly anything involving training training a transformer to do RL, and anything in a kind of simple-ish, ideally discrete environment seems potentially tractable. There's this really great paper from Rehan Shah on capability generalization but objective misgeneralization, where you train a RL model in some environment, deploy it in a slightly different environment, and see that it acts competently but towards the wrong goals. And in that paper, they have this tree grid world and monster grid world environments, which are pretty simple environments. They exhibit this behavior, and I believe the models are two-layer convolutional networks. And it seems like a pretty cool thing that I think someone could get traction in trying to interpret. I'll see what you find.
Yeah, awesome. I also think there was a project from the last interpretability hackathon that looked at some of the reinforcement learning and mechanistic interpretability directions. So maybe that'll be shared as well, and you can check that out.
Yeah. Have there been any questions? Not seeing anything in the chat.
There's a question. How do you define a circuit in a transformer?
Sure. So this is a kind of messy question. I recommend looking up circuit in my Mechinterp explainer. That's neelnanda.io/glossary, where I try to articulate this. My brief definition now would be some subset of the model's activations and parameters that implements some interpretable algorithm. We can say what it starts with, we can say what it ends with, and we can describe the internal computation going on internally. There's currently a bunch of, debate within the field about exactly how you should define this. There's some great work on causal abstractions and causal scrubbing, led by some researchers at Stanford and some researchers at Redwood Research, that try to define a circuit in terms of causal interventions, where you can predict what interventions on the model are allowed or not allowed by your hypothesis, and use this to figure out whether you've got a circuit, which is what the indirect object identification paper did. There's things that involve literally reverse engineering the weights and just reading off the algorithms, which is what I did for modular addition and what we did for induction heads. Though the causal interventions work has raised some pretty compelling critiques of the induction heads, finding they were doing somewhat more sophisticated behavior than just the strict induction circuit we found. And I think a cool project would be looking at the Post and Redwood's causal scrubbing sequence about induction heads, and trying to decode from the weights the more complex stuff going on. Yeah, there's a particular kind of circuit that's most of what we've seen in models, called an end-to-end circuit, where you just look at the input tokens, you look at the output logits on some behavior, and some distribution, and you try to understand how things go from the inputs to the outputs, which is a kind of cool, specific approach. I also think there's a bunch of potential for kind of in-the-model circuits. This requires you to start and end from a thing that is interpretable, which is kind of hard, especially with our current understanding of what features are inside models. Though that is another reason to go and stare at a bunch of neurons and try to figure out what on earth is going on, and what on earth is up with polysemanticity. Yeah, that's my take on a circuit.
Nice. We have another question. So what kind of interaction would you like to see between mechanistic interpretability and other interpretability approaches, e.g. ELK?
That is a good question that I'm not sure I have strong immediate thoughts on. Paul Cristiano, who's one of the main authors on the ELK report, which stands for Eliciting Latent Knowledge, and is about trying to figure out how to get models to faithfully tell us the internal beliefs they have about the world. So he has this post on mechanistic anomaly detection that I think is pretty cool, though I should really go read it in more detail, that I think gives some model on that. Generally, I just feel like we're so confused about what's really happening in networks, and we have so few examples of actually well-understood circuits, that I just want to get anywhere on understanding these models, in particular on understanding neurons. And I kind of don't care that much about the specific alignment theories of change, because I think that just most things boil down to, at least partially, have any idea what we're doing. And the field is just like pretty young and early stage and has lots of low-hanging fruit. But yeah, I'm excited about things that try to study the model's world model, like digging into factual knowledge. There's this paper called Rome from Kevin Meng and David Bao, which introduces this really cool causal tracing technique that tries to reverse engineer what's going on with factual knowledge recall. The paper's mostly about memory editing, but I'm way more excited about the bit where they try to reverse engineer the underlying circuits from an interpretability perspective, and would totally encourage people to go do projects building on that if they're interested in factual recall. I'm also pretty excited about work trying to reverse engineer deception, though I think that's probably a bit ambitious for the current state of the field.
Nice. Any other questions from people?
There is one last question asking if you're wearing a suspender or a backpack.
Ha! Oh, this is a posture corrector. Since I have bad posture and I'm attempting to fix this.
Nice.
So neither. Oh, I just saw some in the chat. Alright, so the question is, when trying to understand a circuit, there's a trade-off between how faithful the circuit is to the actual model, how good its performance is, and how simple it is. Do I have thoughts on principled ways to make the trade-off? Like, we could have a circuit that kind of recovers 80% of the performance and is tiny, or a circuit that recovers 90% that's twice as big. So I don't have a great precise answer to this question. I think that I don't have a great precise answer. I think that both are interesting. There's like the trivial extreme where you have a circuit that contains like 2 heads and it recovers 1% of the performance. I'm not that interested in this. There's the extreme where you have the entire model in your circuit, where it recovers all the performance, but it's incredibly boring because it's so complicated. Both of these suck. Honestly, I kind of feel like you just know it when you see it with the circuits. Or like, I'm interested in both the simplest circuit that has good performance, and in the least complicated circuit that has really good performance, where you include lots of extraneous stuff, like the backup heads in the indirect object identification work. But yeah. I don't know. I'm kind of leery of giving precise definitions for this kind of question, because I think it's really easy to give yourself an explicit metric or definition, and then try to optimize that, and then exploit this in order to find something that's not true to the spirit of it, but true to the letter of it, which, as alignment researchers, is a phenomena we should be very familiar with and very careful about. Yeah.
Wonderful.
Any
All right.
final questions?
I do not see any here, nor online at the moment. So thank you very much to Neel, and we'll jump a bit into the logistics afterwards. Wonderful.
Cool.
Thank you.
I just also want to give the final take that one of my current side projects is trying to write up good educational and intro resources to Mech-Interp. And with many people here trying to be introduced to Mech-Interp by reading my things, I am very excited to get user feedback. And I would love to be DM'd or have feedback put into, I believe, the resource feedback channel that may or may not still exist. And yeah, would really appreciate this, especially takes on things that work particularly well, or ways things can be better, or things you find confusing. Yeah.
Wonderful. Thank
Very
you very
excited
much.
to see what you guys do.
Yes, and we'll set that channel up so people can give all of the resource feedback in the world.